Now that we've worked a fair amount with derivatives, we're ready to take a look at the derivatives of trigonometric functions. And I can't think of any better place to start than with sine x. So the question is, what is the derivative d by dx of sine x? Okay, and we'll give a proof of this a little later, but we can come up with an answer right now. Let's just look at the slopes of the tangent lines at certain places here with sine x. For instance, let's look at x equals 0, right? I can imagine a tangent line in here. That slope to me looks about like 1. So on this bottom set of axes here, let's plot the derivative of sine x and see if we can plot these points together and connect them and see what happens. Okay, so at x equals 0, we have a derivative of 1. So I'm going to go ahead and plot the point 1 here. Now at sine of pi over 2, if I look at the derivative here, well, that to me is looking like a horizontal line because we're right at the top of the function. And what is the slope of a horizontal line? 0. So if I go down to our graph of the derivative, I give it 0 at the point pi over 2. All right, moving on. How about pi? Well, if I look at the point pi on our sine graph, right there, I'm thinking the slope is about -1. Okay, so back down on my derivative graph, I get a point of -1 at pi. And at 3 pi over 2, back on our sine graph, looks like we're at 0 here again because the function turns around, so that must give us a slope of 0. Back on our derivative graph, we're at 0. And finally at 2 pi, back up on sine, I'm thinking we have a slope of 1. That's what it looks like to me. So back down here, I will give us a point 2 pi comma 1 on the derivative graph. And look what we have, right? We can connect these dots, and if we do it a little bit cleverly, right, you start to recognize what this is. It looks like some kind of trigonometric function. Which one? Well, it's 0. It's 1 at 0, 0 at pi over 2. Well, this is simply the cosine, cos x graph. So that is in no way a proof, but it is a proof of concept, at least, that the derivative of sine x is cos x. That is indeed the derivative, and we'll follow up with a more rigorous proof down the road. Let's repeat this process and see if we can get at the derivative of cosine. Okay, so here we have the graph of cosine of x, at least a little bit of it. And the question we're asking is, what is the derivative of cosine of x? And we'll repeat this process again. Just take a look, see if we can intuit what it is without any super rigorous mathematics. Looking at this cosine graph, I'm thinking this has a slope of 0 at x equals 0, at the point 0, 1. Right? It's a horizontal tangent line. That slope must be 0. So down on my derivative graph, I'll put the point 0, 0. So this is d by dx of cos x down on this graph. Okay, at pi over 2, that looks like a -1 slope. So I'll put a -1 down here at pi over 2 on the derivative graph. At pi, we're back to a slope of 0 again. M equals 0. All right, so give that 0 at pi down on the derivative graph. Back to 1 again at 3 pi over 2. So let's see here. Let's get that point. There we go. 3 pi over 2 comma 1 down on the derivative graph. And finally, a slope of 0 at 2 pi. So we're back down to 0 at 2 pi. Well, I see this is looking like some kind of trigonometric function down here in the derivative graph. Let's connect the dots and see what we get. Okay, it's coming around. Well, what function is this? Oops. I'm getting a little... At least try to keep my line somewhat smooth here. It's harder with a writing tablet than it is on like a dry erase board. Okay. It's not sine x, is it? Can you figure out what this is? Pause the video, think about it for a sec. See if you can figure out what this is a graph of. Indeed, it's not sine x, but it is negative sine x. right? It's like sine x, but flipped, rotated about the x-axis. And indeed, that is the derivative of cosine of x, negative sine x. Okay, so we have two derivatives. We've done the derivative of sine and cosine. Two down. We want the derivatives of all the trigonometric functions and eventually all the inverse trigonometric functions. So you can imagine we have a fair amount of work still to do here. Let's work on tangent. Now you may be worried that I'm about to graph tangent and then go through this whole process again with all those crazy asymptotes, but I'm not, though I could, that would be interesting. But instead, we'll just do this, d by dx of tan x. Well, remember tan is sine over cosine, so this is simply the derivative of sine x over cosine x. And if you recall, the derivative of sine is simply cosine. And we just determined that the derivative of cosine is negative sine. So here's our two main derivatives. Well, here we can apply the quotient rule to sine x over cos x. That gives us, okay, low d high, so cos x, d high, derivative of sine x is cos x, minus high d low, sine x, times the derivative of cos x is negative sine x. So I'm just going to make this a plus. And then we have sine x here again, over the square and away we go. That's just the one version of the quotient rule. Over the square and away we go. Cos squared x. Okay, well up top we have essentially sine squared plus cos squared, which we know from the Pythagorean identity is 1. And 1 over cos squared x is actually secant squared x. So there is our derivative of tangent, secant squared x. And of course, you don't want to go through this entire process every time you need the derivative of sine, cosine, or tangent. So you want to memorize these derivatives so that they're on quick recall, because this is an awful lot of reasoning to go through every time you want to use one of these derivatives. So here they are. We've already seen the first column here. We have d by d theta of sine theta. So the derivative of sine theta is cos theta. The derivative of cos theta is negative sine theta. And the derivative of tan theta is secant squared theta. And you can do these in terms of theta or x. It doesn't make a difference. Here we have theta just because we're kind of used to seeing theta with trigonometric functions. Continuing to the second column, we have the derivative of cotan theta is negative cosecant squared theta. The derivative of secant theta is secant theta tangent theta. And the derivative of cosecant theta is negative cosecant theta cotangent theta. Okay, so set all those to memory. There's really no way around it. You just need to know them. So put them on into your brain. Here's something to note. Anything with a co in the original function gets a negative in the derivative. So cosine gets negative sine. Cotangent, negative cosecant. Cosecant, negative cosecant cotangent. So that helps a little bit in encoding this. While we're at it, let's just bring up the trig identities that we need to know at this point to help us through derivatives and really the rest of Calc 1. Right? There's a ton of identities, but there's some that are more useful than others. So here are the ones that are useful for us right now. Of course, there are many trig identities, and every once in a while you may need to grab some obscure identity, but these are the ones that you see the most. Okay, so we have sine squared x plus cos squared x equals 1. That's our standard Pythagorean identity. Another version of that is tan squared x plus 1 equals secant squared x. Then we have our double angle formulas. Sine 2x is 2 sine x cos x, and cos 2x is cos squared x minus sine squared x. And then these last two, for cos squared x and sine squared x, we'll use those more when we get to integration, but we might as well throw it in here now. Now that we're getting everything on the table, let's just add these in. These are essentially the double angle formulas in reverse. So here we have cos squared x equals the quantity 1 plus cos 2x over 2, and sine squared x equals the quantity 1 minus cos 2x over 2. Okay, so lots to remember. Good thing that our brains exhibit neuroplasticity. Knowing these and having them on easy recall will be useful as we move forward in the course.